Welcome everyone. This is episode 8 of the Data Structural and Algorithms course, and today we're going to be talking more about abstract data types, specifically priority queues and heaps. Now to begin with, we've previously talked about queues, but now we're moving over to priority queues. And a priority queue and a queue is exactly the same, except that a priority queue associates a priority for every element in the queue. So, since every element has to have a priority, they have to be comparable to each other. And the functions associated with a priority queue are as follows. Nice. So given some pre-initialized priority queue, starting at 4, then 8, 3, 1, 14, and 22, if we were to pull first, and a queue previously stated, it would just give out the first element, which is 4. However, for a priority queue, in this case, we state the highest priority element is the one with the lowest number. So if we were to pull, we'd see the output being 1, because 1 is the lowest number here. Now if we were to add another element, let's say 2, we would pop it back into the next empty spot, and we'd continue moving forward. In order to move forward, we'd pull another one, and you'd expect, usually a queue is first in, first out. However, we just added a 2, and it's being the one removed next, even though other things have been in the queue longer. Well, it's like this because 2 has the highest priority. And if we were to continue this, and we added another 1, and we were to pull it out, 1 would still be the first one to come out. Then if we continued pulling, then it's just removing the next elements. So we'd take out the 3, the next one would be 4, then we'd have 8, 14, and 22. Nice. Now moving forward, we're going to talk a little bit about trees as a small, quick, separate note. So what is a tree? A tree is essentially a recursive data structure such that the children are below a given element. In this case, you have a parent node, which is A, and a parent node A has children B, C, and D, as well as A is the root node because it is the beginning of the tree. There is a couple of terminologies associated with a tree. The root node is the beginning node. A subtree is a section of the tree. So we can have the subtree BEF, which is a subtree of the whole tree. The next thing we have are leaf nodes. And leaf nodes are essentially the last nodes in the tree, such that they don't have any children. After that, a path is a sequence of nodes to get from one to another. Ancestors are any nodes such that they have a parent in common, and the other ones feel free to look at. So now if we were to move forward a little bit, and let's move forward a little bit more. Now that we have an understanding of a tree, we can use these trees to implement a priority queue. And I have here you can use a heap. But we haven't really talked about heaps. So what exactly are they? They're just trees that have a certain format to them. And in most cases, either the parents are greater than or equal to the children, or vice versa. So there is a parent-child relationship for a tree that gives you a heap. Now let's go over some examples. For a max heap, we have the root node being 8 here, and then we have the children node being 7, 6, and the children of 7 being 3 or 2. The reason this is a max heap is because the root node is the max element inside of the tree, as well as the parent will always be greater than the child node. So let's look at the inverse, which would be a min heap, where the root node will be the smallest one, and the parents will always be less than the children. So let's go through a couple of examples together. The first example is this a valid tree? Well, let's look at it. We have 8, and then the parents are 7. So we're going to assume that the parents are always going to be greater than the children. Well, in this case, is 7 greater than or equal to 3? That's good. And is 7 greater than or equal to 2? So this whole subtree here is good. Now we're going down to more left side. Well, we have, is 3 less than or equal to 3? Yep. Less than or equal to 2? That's good. Now if we look over here, we have 7, which is less than 7 is greater than or equal to 3, and 7 is greater than or equal to 2, so we're good here. Then we have this 2, 3. Well, now in this case, the child is greater than the parent. Thus, this makes it invalid because it does not hold true for this subtree. So now for the next one, let's look here. Is this valid? We have 0, and then everything below it is greater. So we're assuming this is a min heap. Well, that means for 1 should be smaller than everything underneath it, which is true. Then we have 2, and 2 should be smaller than everything underneath it. So this looks correct. And it is. This is a min heap. And with that, we've completed today's talk on abstract data types, priority queues, and heaps. Thank you for your time.